and today we're going to be looking at polar form again, mainly the cis theta form, but let's just start. So first we want to have our imaginary graph, part of z and the imaginary part of z, and I'm going to define a point z, and this point z is equal to two things. I'm going to let z equal x plus yi, and I'm also going to let it z equal r cis theta. So if these two expressions are equivalent, then the conjugate should be equivalent as well. So we're going to look at the Cartesian form first and work out what the conjugate is there. So it's x minus yi. So let's plot that. We are positive y here and positive x, and then z conjugate is going to be down here ish is z conjugate, and we're going down negative y this time, but we're still going the same distance x. So if we were to describe this in the r cis theta form, well, we can take a look. So has the distance from the origin actually changed? No, it's been shifted. These two lines have to be equal. So r hasn't changed. What about the cis theta? Are we the same degrees upwards? Well, no, we're not. We're actually going downwards instead of upwards. So what we have is cis negative theta instead. And if you really wanted to expand this expression out, you can. So this becomes r lots of cosine negative theta plus I sine negative theta. Cosine, whenever you put a negative angle into cosine, nothing actually happens. So this is the same as cosine theta. When you put a negative angle in sine, the value changes to a negative. And that corresponds to our Cartesian form. See that the y value is actually the only thing that is changing here. So now let's look at multiplication in cis form. So I have two z values. Z1 is equal to radius 1 cis theta 1, and Z2 equals radius 2 cis theta 2. And I now want to calculate Z1 times Z2. How am I going to do this? Well, we can write it out as R1 cis theta 1 times R2 cis theta 2. We can get the r's together, so we get R1, R2, and then we have this cis theta 1, cis theta 2 business. So now we're going to have to expand these out. What we get is this. So now that we have this expression, we can actually expand. So we get R1, R2, lots of plus I squared. I'm going to go on the line here. This is still a times. This is still an I squared here. Sine theta 1, sine theta 2. And now we're going to collect the imaginary terms. So here, this is imaginary, this is imaginary. This here with this I squared, we can just turn that into a minus. So what we'll get is the real and imaginary parts of each, and I'm now going to clear this. R2. Lots of cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2, plus I lots of cosine theta 1, sine theta 2, plus sine theta 1, cosine theta 2. And now we're going to have to somehow simplify this expression. So we can simplify it by simply using a clever trick that was found ages ago. We can actually factor these down into this format. And if those two expressions are equivalent, then we can see some real magic happening here. We have a cosine and an imaginary sine, and we can simplify that down. That's Kiz. So we have radius 1 times radius 2 cis of theta 1 plus theta 2. Similarly, we can actually divide our z1 and z2, and we'll get r1 divided by r2, and we'll get cis theta 1 minus theta 2. I now want to go on to powers of complex numbers. That is in Kiz theta form. If we were to times this multiple times to each other, what will happen? We'll get r to the power of 5, and this Kiz theta thing will be times by a factor of the power, because we're adding theta the n amount of times. So we now have this general rule, and we can work out powers of complex numbers fairly easily. So that's all the time that I have for complex numbers. If you have any questions, feel free to leave a comment down below or contact me on social media, and I will see you in the next video.